Second reason that makes it special is that he's not your average scientist like me and others here, but a crossover from being the father of a teenager with another genetic epilepsy to starting a company to fix that one and others. So, Daniel.
Thank you, Anna, and thanks everybody for having me here. For full disclosure, and it's not that I'm not your average scientist. I'm not a scientist, period. Let's start by there. So with that said, my request is that you don't ask me too many complicated questions. But most probably I won't be able to answer them, but anyway. So like Anna said, I have a daughter with Dravet syndrome. As you may know, Dravet is another very severe type of genetic epilepsy. So most of my talk right now is going to be about Dravet, but you'll see at the end why I'm here and why everything comes together. So a few years ago, I got together with another father that many of you might know, Warren Lammert, who's been in the field for many years. And we went to a professor at the Whitehead Institute at MIT, Harvey Lodish. Harvey, previously he wrote actually the textbook on molecular cell biology. He started a small company many years ago called Genzyme. And we went to Harvey and said, Harvey, we'll like your help. We're parents, we're not scientists. We'd like to look for solutions to not only treat, but potentially cure Dravet. As we all know, these genetic epilepsies are more than just seizures. So current antiepileptic drugs just don't do it for us. We might reduce seizures, but like Isabel said and others have said, I mean, the global disease treating all the cognitive impairment and other issues are probably more important than only trying to reduce seizures. So at that time we said, well, Dravet is a complicated disease to treat. It's a large gene. You have to be very careful where you express N1A. You don't want to overexpress, et cetera, et cetera. So we came up with the idea, well, Harvey and other scientists, of using tRNAs and other methods to also modulate mRNA and try to increase protein levels, which at the end, that's what we want to do. So if you think about and by the way, the name Tevard comes from reversing Dravet, which was our original goal. It's still our goal, but as you've seen, we have several platforms that work not only for Dravet, but also other epilepsies and other genetic diseases as well. So if you think about the central dogma where you have DNA, mRNA, and protein, there are many diseases where you have mutations in the DNA that result in insufficient protein. So at the end, the issue that we're dealing with in many of these diseases is that we have insufficient protein. Those are what we call haploinsufficient disorders for a normal functioning of the system or the patient or the person. So given this, we have two potential strategies. One could be, why don't we try and get more protein production from the healthy or the wild-type copy of the gene, like Stoke is doing, like Praxis is doing, and other approaches as well. Or on the other hand, we could try and repair or get a full-length functioning protein from the mutated copy. We have three different platforms, but the one that's more advanced and the one that I'm going to discuss today is the one that we use to try to not correct, but produce a full-length protein from the mutated copy of the gene. And as you'll see with this approach, we can actually treat Dravet, we can treat many other genetic epilepsies and a whole set of genetic diseases as well. Currently, we're actually working, our lead indication is Dravet, and as you'll see, the other epilepsies as well. We also have a collaboration with Vertex, where we're working on Duchenne muscular dystrophy, and we're also working on cardiology. So basically what we're doing, again, going back to the central dogma, we're modulating mRNA, and we do it, at least two of our platforms, by using tRNAs. And tRNAs are critical in the translation process. And big advantages of tRNAs are, first of all, they're very small. So the whole gene that encodes for the tRNA measures 200 bases. So you can deliver them using AV vectors, LMPs, or other methods. So at the end, that gene that we're trying to target, to cure, becomes irrelevant because we're delivering the tRNA. Something very interesting about one of the platforms, which we call the suppressor platform, is that the suppressors, the modified tRNAs that we deliver, are mutation specific. So the same suppressor, the same drug, the same gene therapy that you can use to treat one mutation in one gene, it can be used for the same mutation in different genes. So as you'll see at the end, that opens a possibility for doing a basket clinical trial with one drug for many similar diseases. And suddenly there's been quite a bit of, it's definitely a new modality, which I believe that we pioneered the use of tRNAs for therapeutics, and there's been quite a bit of interest lately because of the potential that they have, that with a limited number of constructs, you can actually treat many different diseases, different types, and in different tissues as well. So again, we have 3 different platforms, but the one that we're going to discuss today is the suppressor approach. I'm sorry, I think I'm missing a slide. Yep, I'm missing a slide, I guess. But okay, so actually okay, so let me just talk about it. So at the end in the genetic code, you have 60 sense codons. Basically, a codon is a triplet. It's 3 different letters in the DNA and in the mRNA, which tell the ribosome when it's reading it, you're going to place this amino acid in the polypeptide chain, which then becomes the protein. And those different codons are read by the tRNA. In addition to the 60 different sense codons, there are 3 stop codons. And the stop codons is a 3-letter code. There are 3 different ones that actually tell the ribosome, you stop reading here. This is where the protein is complete, so the polypeptide chain gets released, and you have a full sense protein. The problem, and I'm going to jump a little bit, is when you have 1 letter changes in a coding, in a sense codon, and then it becomes a premature stop codon. And there are 19 different ways in which regular codon can become a premature stop codon, only with 1 single letter change. So if you think about it, if you think all the problems that one single mutation can produce in a patient, think about this. So at the end, you have 19 different possibilities. The interesting part is that the frequency of occurrence is pretty constant across genes. And if you look at the numbers, there are 2 which are the most prevalent, which is an arginine to a UGA or TGA, and a glutamine to a UAG. And with those, probably between 40 and 50%, as you'll see in Syngap, it's even more than that, you can cover most of the cases with the disease. So I'm going to go back right now. So what does our suppressor platform do? In normal functioning, as you see in the graphic, in the top, you have the ribosome basically looking for the tRNA that encodes for a codon. It places the amino acid in a polypeptide chain, and you produce a full-length protein. The second one, you have a mutated gene where you have a premature stop codon. Remember, what happened is what used to be a regular sense codon becomes a premature stop codon. So the ribosome doesn't find the tRNA that recognizes that codon because there aren't any tRNAs that read a premature stop codon, and it basically produces a truncated protein or a non-functional protein. So what we do is that we grab a tRNA and we modify the anticodon, which is the end, the part of the tRNA that recognizes that codon. So we modify them so it can recognize a premature stop codon. So what you have then happening is a tRNA recognizing the premature stop codon, placing the amino acid in a polypeptide chain. So at the end, you have a full-length protein being produced by a mutated gene. And of course, the natural question, and this one actually I can't answer, is, okay, but you're introducing a modified tRNA that's going to read a premature stop codon. Isn't it going to read also the natural termination codon? And you're going to be producing an extra long protein, which is going to be also toxic. And the question is no. There are multiple reasons, and there's quite a bit of experiments made with ribosome profiling, where actually we show, and others as well, that only in less than 1% of the cases, the suppressor tRNA reads over the natural termination codon. And the main reason is that there are protein release factors that are tethered to the 3' UTR region. So only when the ribosome starts getting close to the natural termination codon, it doesn't read it. So if a mutation is not in the 3' or close to the 3' UTR region, it won't read over the premature stop codon. Again, we already saw this one, and we have quite a bit of data. This is data on cell lines, the Western blots on the left. So we show protein being produced in a non-functional gene with the arginine to a UGA suppressor in this case, and we've actually compared with small molecules that have been touted as read-through molecules like atalurin, also gentamicin, aminoglycosides. As you can see, the suppressor actually produces a full-length protein. The aminoglycosides or atalurin actually doesn't work. We can talk afterwards. I can explain why it doesn't. On the right, you can see an SCN1A channel also. The top one is mutated, and the bottom one, you have the suppressor, and actually opens and closes like it should be. We have quite a bit of mouse data that we have produced, thanks to Anna and the foundation in Spain, which actually produced this mice a while ago. It's a mouse with a premature stop. And the left-hand side, you can see survival assay, like Isabel also described. Again, the uninjected mice at day 21, most of them start dying. We have actually multiple designs of suppressors with multiple viruses, and they substantially increase survival. Some of them have been going for 300, 400 days without any death. On the right-hand side, you can see actually protein levels, mRNA levels measured at P21, more than 100% increase in mRNA. And we've also seen protein levels. These are at day 21, we see 76% of wild-type levels of protein. So if you think about it, we're increasing protein production at 50% on base levels. If you measure at day 50, you have even more higher levels of protein than 76%. So the suppressors work. This is one of the ones that we're working in right now. You can see on the left-hand side, you can see the survival. You can see also what we do heat-induced seizure assays, where you start increasing temperature in the mice, core temperature, and you see when they seize, and we see shifts of up to 1 and 2 degrees Celsius. So we've seen seizure thresholds go up. If you think about Fahrenheit, 109 degrees, which at the end, nobody gets to that levels of temperature. And with the same constructs, you see increased mRNA levels and increased protein as well. Okay, so you might think you're talking about Dravet, so why are you presenting in Syngap? So this graph, which is a heat map, you see on the left-hand side, you see multiple epilepsy genes. The first column, it tells you the percentage of cases within that disease that's caused by nonsense mutations. If you look at top, Dravet, it's about almost 20% of all cases is caused by nonsense mutations. If you go to the bottom, you see that actually 35% of all cases in Syngap is caused by nonsense mutations. If you look at other indications like XCXBP1, it's about 20% of all cases. Second column to your right, where you have the purple arrow on the bottom, you can see the proportion that's caused by an arginine to a UGA mutation. Within Syngap, within that 35% of all nonsense mutations, over 50% is actually one mutation, which is an arginine to UGA. If you jump to the other column that's shown with the arrow, which is a different suppressor, will be a glutamine to UAG or TAG, it's about 23%. So with actually two suppressors, and we've been working on a concept that we call the bi-stop and the tri-stop, we actually package two different suppressors in one AV vector. You can treat actually over 50% of the Syngap population that has a nonsense mutation. So our plan, sorry, there's some slides missing here, but okay, sorry about that. I think I sent one presentation, I probably sent the wrong one. That's okay. But anyway, what we're doing right now, we're working on a basket clinical trial. So our lead indication is Dravet. We have most of the data in Dravet. We're in non-human primates right now, and we're going to be filing pretty soon for IND. As we do that, we've been working with a foundation which has been generating mouse models with two of the most prevalent mutations, the arginine to UGA and the glutamine to UAG. And then the idea is to go 2 clinical trials with one construct for several epilepsies at the same time, where we're measuring similar endpoints. So the idea will be then to do a joint trial for Dravet, probably Syngap 1, hopefully STX-BP1 as well, SCN2A, and CDKL5. And if you think about it, there are great economies of scale. You only have to do tox once with a construct. We'll probably do it at one time. You file a package, and then you can show, if you can show efficacy for the other indications, then you can do a trial with several indications at the same time. And yeah, this one I think I mentioned it. I wasn't going to talk. Part of the team. Yeah. Okay, that's it. Sorry about that.